Hi there. In this video, we're going to be talking about cylindrical and spherical coordinates. In mathematics, people are always looking for easier way to do things. Integration is quite difficult at times, and we can end up with integrals that can be hard to evaluate. So what people do is that they change the coordinate system. Often when you change the variables to be in terms of one variable and change it to another coordinate system, we find that the integration becomes much easier. So cylindrical and spherical coordinates are two different coordinate systems. The variables are changed to be in terms of other variables, and what happens is that certain figures become much easier to evaluate, that is in terms of integration. So we can start off with cylindrical coordinates, and we would use cylindrical coordinates when there is an axis of symmetry. The integrals become much easier to evaluate when there is. When I mean axis of symmetry, I mean, for example, if you have a simple parabola, then we can see that the y-axis is actually an axis of symmetry. And in 3 space, we can think of the z-axis as being the axis of symmetry. And that's what we're going to look at now. So there is a change of variables that goes from x, y, z to that of r, theta, z. So from x and y, we transform it into r and theta. So this change of transformation, this change of variables is actually the same as the change of variables to polar coordinates, except that now we in 3 dimensions, and we're also including the variable z in the polar coordinate system. So if we have a cylinder, and that's what we're doing, we're converting to cylindrical coordinates, and if we just take a point on the cylinder, a random point that is, and we think about its projection on the xy plane, the height of this point, that is from the base to the point, is just z, so that doesn't change in this coordinate system. Z remains the same. What does change is the x and y, and what happens is we consider the r, as is the case with polar coordinates, to be the radius from the point of origin to the point on the cylinder. So that's what r is. And then we also include theta. So theta is just the distance from the x-axis to the point itself. So that's x, y, and z. So if we do our conversions, if we convert to the x and y coordinates, we can see that x is simply r cos theta, as was the case with polar coordinates. So we can understand this by just looking at the basic triangle. So there's our triangle, there's our angle theta, and this is x and y. So, and that's r. So of course cos theta is x over r. So x is r cos theta. So y is also done in similar manner. So y is r sine theta. Z just remains as z. There's no transformation of variables there. And r, by the theorem of Pythagoras, is just the square root of x squared plus y squared. And of course, theta is arctan of y over x. So this is the transformation of variables, and it's actually quite a simple matter to do this conversion. If we're given a point, any point, and if we want to convert it into cylindrical coordinates, all we just do is use these equations. So this is very nice and easy to do, but the whole point of converting something to cylindrical coordinates would be to make the integration easier. That is the whole purpose of why we are performing this exercise. So how do we actually now integrate using cylindrical coordinates? Well, as was the case in the normal coordinates with x, y, and z, all we do is we take a volume element. So we have a volume element, and of course it's just dy, dx, and dz, and then all we do is we integrate. It becomes a triple integral of dx, dy, and dz. So all we do is we do the same thing with cylindrical coordinates. We take a volume element and we multiply everything by this change in variables. So our volume element, if we can just draw it around the point, would be something like that. We would take the volume element and then we're going to integrate it around our various boundaries. So that has been just drawn here. So we can see that radius is, well, it's the same both in the segment and its projection in the xy plane. So that is the radius, and this is a differential change in the radius. So that's dr, and of course that's the same with projection, that's dr. And this angle theta, so this is a change in the angle theta, so that's just d theta, and it's the same here on the top. So that's d theta. And this other part of the curve, so that's r d theta. It's easy to understand this. If we have a circle and we take a segment of the circle, so that's the radius. So when this segment of the circle, or when the length of the circle equals the radius, then we define the angle to be 1 radian. So theta is equal to 1 radian when this length, this arc length of the circle equals the radius. So if we think about increasing the length of the arc, then we can see that that length of the arc itself is simply equal to the radius multiplied by the angle between them, because we have defined the angle to be 1 radian when the length of this arc is the same as the radius. So if we are to extend this arc some more, then we can actually see that this angle is now 2 radians. And if we extend it even more, then we can see it's just about 3 radians, or exactly 3,14 radians. So that's why we say that this half circle is actually pi radians, or 3,14 radians. So pi radians is about 180 degrees. It is 180 degrees. But the whole point of this was to show that the length of the arc is equal to the radius multiplied by the angle. So here we can see that this is our radius length, dr, and our angle is d theta. So the length of the arc is r d theta. So that's r d theta. So we can see now that we have everything that we need to compute the volume element. We can just take length times the breadth times the height. The height is still, of course, z. There's no change in variables there. So what is our volume element? It's just simply r dr d theta multiplied by dz. Length times the breadth times the height. So of course the volume is simply just the triple integral around any region of r dr d theta dz. We can illustrate this in a basic example, and that example is we have some kind of plane figure here, This figure is basically the first octant. So, in the Cartesian plane, we would have 4 quadrants, 1, 2, 3, 4. So in 3 space, we would have 8 quadrants. So each one is called an octant. So the first octant, we're considering just the first octant. We're saying that this figure is bound in the first octant, where x, y, and z are all positive. And what we're considering is the cylinder x squared plus y squared is equal to 4, and also intersecting with the plane z is equal to 6 minus xy. So we can see that this is our cylinder. We can see the shape of the cylinder, and we know that the x and the y intersections is equal to 2, because that's how we draw our circle. This is x squared plus y squared is equal to 4, and we know that it intersects everywhere at 2. So we have the shape of our cylinder. So now the other thing we just need to take consideration of is the other plane that's bound by. So that's z is equal to 6 minus xy. So that would be this plane on the top. We can see that it's not distinctly a cylinder, but it has a somewhat of a parabolic looking shape like that. So this is 6 minus xy. So how do we find the volume of this particular shape or this particular figure? Well, we just do it exactly as we had done it previously. We take our volume element, and we integrate it. The only thing we need to take consideration of is how we're integrating it. That is our boundaries. So we're integrating firstly along the z-axis. We can think about it. Where are we integrating from? We're integrating from 0. We can see that we're starting off at 0, and then we're going all the way up, and then where are we stopping at? We're stopping at the plane at which it's bounded, so that we're stopping at z is equal to 6 minus xy. So that is our z boundaries that we're integrating. We're integrating from 0 to 6 minus xy. Then we need to think about r and theta. So r is just the radius of the circle, and we can see that the radius of the circle is 2. So we're integrating from 0 to 2. We're stopping at 2. And then lastly, theta, the angle. Theta is going from 0, we can think of 0 here, and it's going all the way and stopping at the y-axis. So this is actually 90 degrees or pi over 2 radians. So theta is going from 0 to pi over 2. And what we're integrating is r dr d theta dz. So now we proceed to evaluate this integral, but we first have to convert this xy into the variables of integration. And the variables of integration are r and theta. So it's a simple matter to convert from x and y to be in terms of r and theta. We would remember that x is equal to r cos theta and y is equal to r sin theta. So 6 minus xy is simply equal to 6 minus r cos theta times r sin theta. And this is just equal to 6 minus r squared sin theta cos theta. So we can replace that. So this is now equal to the integral from 0 to pi over 2, 0 to 2, and then from 0 to 6 minus r squared sin theta cos theta. So this is a boundary of this is the upper bound. And what we're actually integrating is r I'm just going to write the dz first. dz dr d theta. So if you're integrating first with respect to z, all this just becomes is z. R is treated as a constant first. So we would just substitute in this 6 minus r squared sine theta cos theta. So that's what we'll do now. Okay, this should not be y is equal to. So if we do that, we just get from 0 to pi over 2, 0 to 2, and then r multiplied by z, and just z is 6 times 6 minus r squared sine theta cos theta. So we can just multiply it out now while we're at it. So we get 6r minus r cubed, basically that r multiplied by this upper boundary, sine theta cos theta. And then dr d theta. So proceeding with this integration, and now integrating with respect to r, what we have is the integral from 0 to pi over 2. The integral of 6r is simply 3r squared minus 1 over 4 r to the power 4 sine theta cos theta. And of course, this is integrated from 0 to 2. And then evaluating this by substituting in 2, what we get is 2 squared is 4, 4 times 3 is 12. And then 2 to the power 4 is 16, 16 divided by 4 is 4. And sine theta cos theta remains as is. And lastly, this is just integrated with respect to theta. And when we do that integration, integral of 12 is just 12 theta plus the integral of sine theta cos theta is just cos squared theta and of course we need to take consideration of this 4, so we would multiply it by 2. We can understand that this is true just by differentiating cos squared theta. So the derivative of cos theta is sine theta. So sorry, that's minus sine. So that takes care of the minus here that we see. And of course we have that 2. So 2 times 2 is 4. And of course the derivative of the inside function is what gives us that sine theta. And the outside function is just the cos theta that's remaining. And this is integrated from 0 to pi over 2. So what's left when we integrate this is simply 6 pi minus 2. 12 times pi over 2 gives us 6 pi, and the derivative of pi over 2 is 0, and then we substitute in that 0 again. 0 times pi is 0 times 12 is 0, and the cost of 0 is 1, and that's how we get that minus 2. So when we multiply it by 2, then we get the minus 2. So that is how we would evaluate this particular integral. So if we wanted to integrate this particular figure using normal coordinate systems of x, y, and z, what would our integral look like? We can see that we would have to integrate still as it would be with z. It goes from 0 to 6 minus xy. Now we would need to integrate with respect to y, and we have to go from 0 to y, and we stop at this function. So we need this value for this function, and we know that it's given by the circle x squared plus y squared is equal to 4. We'd have to solve for y, so y is equal to the square root of 4 minus x squared. So we'd have to integrate from 0 to the square root of 4 minus x squared. And then lastly, we'd have to integrate from 0 to 2, dx, dy, and dz. So we can see that this is a much more difficult integral to actually evaluate if we were to proceed with it. It's actually longer to do it this way than it is just to use cylindrical coordinates. So using cylindrical coordinates has actually made it easier to evaluate this integral. We're now moving on to another change of variables. We're now going from the normal coordinate system x, y, z to that of spherical coordinates. Spherical coordinates is somewhat different from what we have looked at so far. There was some familiarity with cylindrical coordinates because it involved polar coordinates. The r and the theta was something that we can recall. Spherical coordinates is a bit different, and the change of variables might not be something one would be entirely familiar with. So from x, y, and z, we're instead moving to rho, theta, and phi. So what is this rho, theta, and phi, and how do we actually make that conversion? Spherical coordinates is generally used when there is a point of symmetry. So we can think of a sphere and everything is symmetrical about a particular point. That is, if we think about the sphere that's been drawn here, we can see that everything is symmetrical about the point of origin. So that's what is meant by point of symmetry. And we find that when we convert an integral to this particular coordinate system, it's actually much easier to integrate. All that we need to do is understand what this transformation is, that is the transformation of the variables, and understand how to set up the integral. So let's look at what these variables are in spherical coordinates and how do we go about deriving them or understanding how they come about. So let us have this sphere in the xyz plane, and we're going to now define what each of these variables mean. So firstly, we had this rho. You remember that instead of x, we're now going to have rho. So what is rho? Well, rho is the distance from the origin to our point. So our point is on the sphere. We can think of it as being on the outer edge of the sphere, and the distance from the outer edge of the sphere to the origin is called rho. So rho is here. We can just write it, and we can just understand it's the distance from the origin to our point. And then we have theta. So theta remains somewhat as it was from cylindrical coordinates, but instead of the angle to a point, it's actually the angle between the projection of the point. So what I'm saying is, if we have this point, and then we project this point on the xy plane, and then we define some other variable, maybe r to be the distance from the origin to the projection of the point. And the angle theta is the angle between the x-axis and r. So there is a difference here now between r and theta. There's a difference between r and rho. Rho is the distance from the origin to our point on the sphere, whereas r is the distance from the origin to the projection of the point on the xy plane. That's very important to note. So lastly, what we have is just the angle between the z-axis and rho. So we're creating a new variable there. This is the angle between our point, rho, the distance between the point on the sphere and the origin, and now that angle between the z-axis. So that is called phi. So I'll write it here, phi. So these are our three variables, rho, theta, and phi. So how do we do our conversions now? How do we convert between x, y, and z and rho, theta, and phi? So let's draw this triangle, okay? So the first thing we need to understand is that we have a right angle triangle. So that right angle triangle is rho, r, and z. So there's our right angle triangle here. Rho is the hypotenuse, r is on the xy plane, that's the base of the triangle, and z is the height of the triangle. So we can draw it like this. We have rho, we have z, and we have r. And this angle here, this is actually phi. So we're saying that this angle here is phi. Remember, in geometry, there is something called alternate angles. So if this angle here is phi, then this angle here is also equal to phi. You can see that it makes an inverted N shape. So that angle is equal to that angle. Okay, so now we can just write our normal trigonometric ratios. If we take cos of phi, we can see that cos of phi is equal to z over rho. So that means that z is equal to rho cos phi. Z is equal to rho cos phi. So what else? Now we can think about the projection on the xy plane, because we need to move from x and y to that of rho, theta, and phi. So there is an angle that's formed on the xy plane. We can understand that quite easily. There's a right angle triangle here. And we have y. So the distance between that point and our projection is just y. And the distance between our projection of the point to the y-axis is simply x. That's y and that's x. So if we draw this triangle, we'll draw it here. We can see that this angle is theta, and then we can see that the base is x, and we can see that the height is y, and r is as it is. So this is our triangle that we used to, and we can simply evaluate x and y as we are done with cylindrical coordinates. So we can see that x is equal to r cos theta, and that y is equal to r sine theta. But there is a problem here, and that problem is that we are not working in terms of r anymore. R is not the variable with which we're going to be converting to. Instead, it's phi. Phi is what we want. So we need to move between r to phi. And how do we do that? Well, we can just use our first triangle that we have done here. And it's a simple matter just to see that r is actually rho sine phi. If we just take sine of phi is actually opposite of our hypotenuse. That's just r over rho. So r is equal to rho sine theta. So we can do our conversions now. We can simply see that x is equal to, we substitute in rho sine theta for r. So x now becomes rho sine theta multiplied by, instead of theta here, it should be phi. My apologies. So r is equal to rho sine phi, and then lastly cos theta. Then we would do y. So y is equal to r. So we write rho sine phi and sine theta. So that's done. We can now convert between all our variables. Everything is known. If we have a coordinate x, y, and z, how do we convert to rho, theta, and phi? Well, we can see everything. Z is equal to rho cos phi, x is equal to r cos theta, and y is equal to rho sine phi sine theta. So everything is known. All the conversion variables are known. So the last thing that we need to do in order to be able to evaluate is simply find the integrals. And as it was the case with everything we've done so far, we just need to take a volume element. And the volume element will look something like that. Now, we need to find the volume element like that. We'll just draw that out separately on another graph. So now what we're going to do is find the volume of a plane figure using the coordinates that we had just described. That is spherical coordinates. So we took this point on the sphere and we have now expanded it to be a volume element. We're now going to label each of the sides of this volume element in terms of the variables that we had just defined. So we saw that rho was the distance between the origin to the point on the sphere. So if we have a differential change in that point, then that length is d rho. So I'll just repeat that one more time. We have the point in the sphere, and if we have a differential change, then that must be d rho. It's just as how we had dr. So rho is actually the radius of the sphere, and this differential change is d rho. So anyway, we also saw that the angle between our point and the z-axis was called phi. So this angle here of this differential element is actually d phi. So what that means is that if we have a radius, so the origin to the point on the sphere, and that's rho, it means that this little arc length must be rho d phi. So I'll just write that here, rho d phi. Just as we had r d theta, we have rho d phi. So I'll just write that here. We have our little element, that's d theta, that's r. This is r d theta. So this has changed somewhat now. So here we have d phi and we have rho. So that must be rho d phi. So lastly, we have our length of this volume element. We have the breadth of the volume element. So we now kind of need like this, we have the height of the volume element. We also have the length. We just need the breadth. So we need this part here. So that's what we need. And how do we get that? Okay. Well, if we think about it, we took our projection on the xy plane of a point, and then we saw we had r, that was what r was, and then we also saw we had theta here. So we can think of this on the top as well. So that length is r, and the angle is actually theta. So here we have d theta, and here we have r. So the length of this, sorry, that's a poorly drawn r. So let me rewrite that r again. So it means that this length is actually r d theta. However, we don't express anything in r anymore. We saw just now that r was actually equal to phi, r was actually equal to rho sine phi. So we do this change of variables. So that's actually equal to rho sine phi sine d theta. So now we have everything to compute our volume element. So dV is equal to, firstly, the length, breadth times height. So firstly we have d rho, okay, multiplied by rho d phi multiplied by the width, which is actually rho sine phi d theta. So I'll just write everything. We have rho multiplied by rho. So we have rho squared. Then we have what we have? We have this sine phi. Sine of phi. And what's left is d rho d phi, and d theta. D rho, d phi, and d theta. So our volume is just the triple integral of this particular function. It's the triple integral across some region of sine phi, rho squared sine phi, d rho, d phi, d theta. We can illustrate the use of spherical coordinates to find the volume of just a hemisphere. A hemisphere is just half a sphere as has been drawn here. So we find the volume, we can see that it's simply just the triple integral, as we have done before, of rho squared sine phi d rho d phi d theta. It doesn't matter in which way we write the order of integration. What does matter is how we define our boundaries. So we can just give it an arbitrary variable, that is the radius of the sphere. We can just say that the radius of the sphere is c. So phi is actually going from 0 to c. So the first boundary, which is rho, it's going from 0 to c. Then we can perhaps think of, we can look at theta, for example. Okay, let's integrate with respect to theta. So let me just reverse this order of integration here. Let's go with theta first and then phi. So theta, as you would recall, is the angle between the x-axis and whatever point we're considering. And we can see that it's actually a full circle. Okay, it's a full circle. So theta is actually 2 pi. So it's going from 0 to 2 pi. And then lastly, we think of phi. Remember what phi is? It's actually the angle between the z-axis and the plane figure. So you can see that actually phi is actually going from 0 to pi over 2. Pi over 2 and then rotated 360 degrees. So pi over 2, that's what phi is, this angle, and then rotated 2 pi radians or 360 degrees. So that's why we go from 0 to 2 pi, that's this full circle here, and 0 to pi over 2, that is the angle between the x-axis and the radius. Sorry, the z-axis. So now we can simply just evaluate this integral. So firstly, we integrate rho squared. The integral of rho squared is just 1 over 3 rho cubed. So let's just write our outer integrals, 0 to pi over 2, 0 to 2 pi, and the integral of rho squared is 1 over 3 rho cubed, and this is just integrated from 0 to c, and then we have d theta, d phi. All we do is we just substitute in c. Sorry, I missed out a sine phi here. So let me just write that. Sine phi d theta d phi. I'll just drag the screen across so you can see it. So now we just proceed with our integral as you would normally do. So the integral of in theta is just everything else remains constant, so we just write theta. So we have the integral from 0 to pi over 2, and the integral of all of this is just theta because everything else is constant. So we substitute in c here, and we have 1 over 3 times c cubed. And then the integral of d theta is just theta. And then theta is going from 0 to pi over 2, sorry, 0 to 2 pi. And lastly, d phi, or rather sine. I keep forgetting the sine, the phi, sine of phi d phi. So all we do is we just substitute in 2 pi L. So when we do that, we get 2 over 3 pi times c cubed. Let's just write that out. 0 to pi over 2. We substitute in 2 pi into theta, and then we bring it out, so we get 2 over 3 pi times c cubed sine of phi d phi. So lastly, all we do is integrate sine of phi, and when we do that, the integral of sine is minus cos. So we have 2 over 3 pi c cubed times the integral of minus cos phi from 0 to pi over 2. And of course, the cos of pi over 2 is just 0, and the cos of 0 is 1. And you put minus because because the lower boundary, so this becomes positive 1. So what we're left with is simply 2 over 3 pi c cubed. Most people would remember, if they have studied maths at various levels, that the volume of a sphere is just 4 over 3 pi r cubed. We can see that it's kind of the same formula, but we looked at a hemisphere, we looked at half a sphere. So if we just divide this by 2, then we get 2 over 3 pi r cubed, which is actually what we had just done here. So this just illustrates the point that we can very much easily evaluate complex integrals with complex equations if we can actually just do this transformation. Because think about if we had to actually do this in terms of x, y, and z. You would remember that for a sphere, it's described by x squared plus y squared plus z squared is equal to c squared. We would first have to integrate with each specific variable, and you can see that it's much more challenging to do it like that. So if we just do this transformation, we can do it quite easily. So this was a sphere of constant density. If we have variable density, then we have to take that into account as well, because instead of just having rho will be a function. So the density would be a function. So if we have to compute the mass, the center of mass, the moment of inertia, it would be a more complex looking integral, but the principle remains the same. All that we would need to change is basically the order of integration. If we're integrating a hemisphere, then we're integrating theta from 0 to 2 pi. If it's just the top half of the sphere, then we're integrating phi to be between 0 and pi over 2.